Hello students, in this video we'll prove the Casorati-Weierstrass theorem regarding the behavior of a holomorphic function near an essential singularity. So this is the Casorati-Weierstrass theorem. It states the following: it says, suppose f mapping omega minus p into c is holomorphic with an isolated singularity, with an isolated essential singularity. So it's not a pole, it's not removable, it's essential at z equals p. Then the image of a neighborhood f of d p r minus p. So I take any neighborhood, right? I take a disk centered at p of any radius I want, r, subtract off p so I can actually plug it in, right? Is dense in C for any r. Okay, that's wild, because what it says is, if I look at a neighborhood of the essential singularity, no matter how small of a neighborhood I look around that singularity, f maps to almost basically essentially everything, a dense set in the complex plane. There, it spreads out very far. And there's actually a much better version of this theorem, a much more advanced version, which we'll prove later, which takes a lot of machinery, called Picard theorem, Picard's great theorem, which is in a neighborhood of essential singularity, holomorphic function takes on every complex value, with one exception, infinite times. Beautiful, right? Of course, there's a continuity component there, which we don't quite get from Casorati-Weierstrass, okay? Okie doke, what does this mean now? So before we prove this, let me remind you what density means, right? Recall, E, a subset of C, is dense if for every, let's say for every Q in C and R greater than 0, D, Q, R, the disk centered at any complex point you want of any radius, intersect E is not empty. So E intersects with every single disk centered at every single point on the complex plane, right? You might say, how is that possible, right? The good example to think about is think about the rationals cross the rationals in R2, right? The rationals are dense in the real numbers, and so therefore the rationals cross the rationals are going to be dense in R2. And R2, if we think of the complex plane as R2, then if I look at rational plus I rational, right, another rational, that set would be a dense set in the plane that's not, which is missing quite a lot, right? So the zero measure set. That's what it means to be dense, okay? Now, what would mean if a set was not dense? It would mean I can find a Q and I can find an R such that E does not meet it, right? That's the idea, right? So that's what, if you're not dense, E not dense, sometimes I feel pretty dense. Right? Just kidding. Not dense if what? If there is, if there are, not is, that's why I feel dense sometimes. I can't do grammar correctly. If there are Q and C and R greater than 0, such that D, Q, R, if I can find them, such that intersect with E is empty, right? Good. All right, so that's what it means to be not dense. So how do we prove Casorati-Weierstrass? Here goes the proof. Suppose that for some R, f of d p r minus p was not dense. Okay. Then there is a Q such that in C, such that f of z minus q, there's this q and then let's say delta greater than 0 and delta greater than 0, such that what? Such that this is greater than delta for all Z in the disk P, R, but not P itself. Okay? That's simply just a definition of what it means not to be dense, right? I'm just strictly using that definition. Here's density, here's the complement to that definition, and I'm just using the complement of that definition. That's all I've done so far, okay? Good. Alrighty, and so now what am I going to do? So now I'm going to define a function, define a new function, as is typical in this business. Define a new function, g of z, which is going to be 1 over f of z minus q, okay? Then by this inequality over here, this implies that modulus of g of z is less than, the reciprocal is going to be less than 1 over delta, and that implies that g is bounded in the neighborhood of what? In the neighborhood of P. And that says that G has a removable singularity at P, right? So G, hence, G has a removable singularity at Z equals P. Okay, good. Now, therefore, what can we say? I can therefore say, by taking the reciprocal, that f of z minus q is going to be 1 over g of z. And therefore, f of z is going to be q plus 1 over g of z. Okay? Now, since g is a removable singularity, I can plug p into g, right? So if g of p, there are two cases. If g of p is not equal to 0, well, if g of p is not equal to 0, that says that f is defined, f has a removable singularity. Implies f has a removable singularity. F has a removable singularity. At z equals p. That's not possible. That's a contradiction. So g of p has to be 0. So g of p is equal to 0. But that implies what? If g of p is equal to 0, that says that f has a pole. F has a pole at z equals p. That's also a contradiction. So it's a contradiction in every case, which means what? Which means my assumption that I could find a q such that this was true for all z in this disk had to be false. So it's false that this f of dpr minus p, it's false that that set is not dense. Therefore, that set is dense. And that proves Casorati-Weierstrass. Now, this result is fairly simple, right? It's just a density result, because I say you're moving away from a particular point for all d in this disk. What we can't necessarily say is we can't say that without further analysis that you might be able to actually attain a given point in the complex plane, except with one exception, right? And that's the weird thing about what is that one exception, right? So to think about that, you can think of this function over here. If you look at the exponential of 1 over z, right? This attains every complex number, maps to every value, every w in c, but it misses what? It misses 0, right? The exponential cannot be 0, right? In other words, so that's an example of an essential singularity. This has an essential singularity at 0, and it hits every complex number, because you can easily figure out how you can find an explicit formula for doing that, right? It's every complex number but 0. So in other words, this function gives us an example, shows us that something a little bit stronger, potentially something stronger than Casorati-Weierstrass is true, and this functions are a prototypical example of something that has an essential singularity, and we'll use this idea when we start to examine Picard's theorem, right? Of course, what we want to do, we'll first approach Picard's theorem through some extra assumptions, right? Like super exponential assumptions, which make the proof a lot easier because the actual proof itself involves analytic covering maps and involves some topological properties of the complex numbers that are a little bit tricky to handle at first sight. So we'll build up some machinery before we actually tackle the Picard theorem, but this should give us a sense of the structure of a holomorphic function around an isolated singular point that is an essential singularity. So the behavior near essential singularities is very strange. I lose all forms of injectivity, and I basically get lots of sort of wild behavior, and so we'll really examine this carefully in further videos. Thank you very much.